Hi guys, welcome to the first part of analog electronics lectures. So in our today class, we are going to discuss about, that is, we are going to solve problems which are related to BJT. I hope you all know the expansion of BJT, that is bipolar junction transistor. So basically, what we are doing in bipolar junction transistor and what are the fundamental basics that are required. I told that we are going to learn this complete concept just with the help of problems. So how we are going to make it happen? So what we are going to do is we are going to cover all the concepts, important concepts, not 100% because it is completely problem solving session. Here going to cover maximum possible concepts through problems. So you just try to understand how to apply all these things and how to learn this. I need only one support from all your sides. So during the class, what you all have to do is just try to suppose if you are applying the concept for one problem, you have to apply. You should learn how we are applying that concept into the problem. I will be teaching you step by step. Just learn the procedure and try to apply the same procedure for all other problems. Maybe you may face different questions. Definitely it will happen. But you will not face other concepts. In the same concept, they will be giving you different questions. Okay. So let us start from fundamental basic. Just what we are going to do first is we are going to learn about the basics of BJT just through problems only. I'm just asking you how we are designing the BJT. To design the BJT, what are the things that we require? Like some people are saying that, sir, to design BJT we need diodes, or to design BJT we need some other device. I'm just asking in that point of view, do you have any fair idea about it? How we are basically designing the BJT? What are the components that is required for that? Let us go one by one. I will be teaching you everything. So let us take the first one. See, basically, in order to design the bipolar junction transistor, that is BJT, we should learn a very basic about diode. Basically diode will be having two terminals. One is called anode and another one is called cathode. And how we are representing the diode? இப்போ நீங்கள் எந்த இடத்துல பார்த்தீங்கன்னாலும் சார் in analog electronics there are so many places where we are discussing about this diode. இந்த டயோடுக்கு ரெண்டு டெர்மினல் போட்டிருப்பாங்க. One is called anode and another one is called cathode. Now if you check inside this property, one side we are having cathode, this strip is representing the cathode, this triangular is representing the anode, this triangular is representing the anode. Okay sir, but if you expand deeply inside, we can show there are two type of property inside the diode. One is n layer, another one is p layer. What is this n layer and what is this p layer, sir? Basically n layer will be having more negative charges, that is called n layer, and if you focus into the p layer it will be having more positive charge. Okay, so here we are categorizing it into two parts. One is this negative positive means what, sir? Basically this indicates the number of electrons carried by this layer. We know in our electrical device basically we are creating this flow of current just with the help of electrons and holes. Yes or no? These two people are only supporting us. They are traveling from one place to another place, so that experience is simply called current. This is called electric current. Then we are converting into mechanical energy. In case of load side, again in sending in we are converting the mechanical energy into electrical energy. We are driving this electron. So everywhere in electrical we will be discussing about this electron and positive charge and negative charges only, simply we can say. Okay sir, So here also in this analog electronics, we are going to design certain applications, electronic applications with the help of certain electronic devices. So we are going to learn how these devices are basically performing their operation in a desired way that we are expecting. That's what we're going to do here. So let us start from this fundamental basics. So in order to design all the desired components according to our applications, we need a primary device that is called a diode. That diode is basically having two layers. One is called a positive layer and another one is called negative layer. Now what is the actual meaning of this negative layer? This person is carrying more negative charges. This person is carrying more positive charges. Just observe my word. I am telling that that person is carrying more negative charges. I am not telling that this layer is carrying only negative charges. So basically what will happen is, if any layer represented by n, it means that layer is having more negative charge and very less number of positive charge. Definitely you can observe the effect of positive charges also, but the number of charges, number of positive charges will be very less. That is the conclusion here. Okay sir, that is fine. Similarly, if you observe the positive zone, in the positive zone what you can observe is, sorry guys, more number of positive charges you can observe. So more number of positive charges means what? You might be thinking that sir, more positive charges means automatically. Yes, you have to think in this way only. So this device will be carrying more positive charges and a very less number of negative charges. That's all. That is the difference between these two. Fine sir. Let us continue. Now I am calling. Suppose if your positive layer, now you understood right? Positive layer means it will be carrying more positive charges. That more positive charges is often called majority charge carriers. And if your device, if a layer is having very less number of charges, then that charge carrier is called minority charge carriers. So now what is the difference here? Majority, minority means these words significantly indicate the number of charges that we are carrying in a particular layer. So now finally what we have to understand is, suppose if you are having any more number of layers, what people used to do is they will be representing it by plus and minus. Suppose if I am putting P, P indicates positive charge. But in the power of P, we are putting plus and minus. What is the purpose of that plus and minus, sir? Plus means a particular layer is carrying more majority carrier, that is more positive charges. That is called majority charge carriers. That layer is having more positive charges. Suppose if it is represented by P minus, then that layer is carrying minority positive charge carriers. Minority means in that layer, the representation or the doped amount, concentration, value of negative charges is very less, sorry, positive charges, and its count is very less. Negative indicates decrement, positive indicates increment. So if I am taking negative charge, in the same way you can say negative plus means negative charges. The person who is carrying negative charges is very high. The concentration, the doping concentration of negative charge is very high. Suppose if I am representing it by n minus, then automatically, sir, it's very easy now. Minus means what? Decrement. In a particular layer, negative charges are available, sir, but its count is very less. That is called minority negative charge carriers. So this is majority negative charge carriers. So this is how basically we are considering the effect of electrons and positive charges wherever it is required. So finally what we understood here, we are designing the diode with the help of positive and negative charge carriers. It is carrying two layers, one is N, another one is P. So this diode, now you might be thinking in opposite way. Sir, நீங்க எதுக்கு N first வந்து எதுக்கு நம்ம N எடுத்துக்கிட்டோம், next எதுக்கு sir P எடுத்துக்கிட்டீங்க? You can also see. First I have taken P, first I have taken N, second I have taken P. So this diode is simply called NP diode, NP junction diode. We are calling it as NP junction diode. What is the junction, sir? Junction is nothing but meeting point of N layer and P layer. Sir, meeting point, are they traveling somewhere? No, they are not traveling actually. Meeting point in the sense, see, I am taking one N layer here. I am taking one P layer here. I am going to merge them together. See there, this layer are going to be merged together. That is called a meeting point. Yes or no? But our friends போறோம் அப்படினா, நம்ம friends வந்து வேற ஒரு பிளேஸ்ல இருந்து வந்துட்டு இருக்காரு, நம்ம எங்க இருந்து போறோம் அப்படினா, we are going to meet at a particular place. Suppose some of my friends are coming from Maharashtra, I am going from Bangalore, and we are going to meet at Chennai. So Chennai is our meeting point, that is called a junction point. Like that, this N layer and P layer are going to meet together at a particular point. That particular point is simply called a junction. It's really quite interesting, right? Yes, sir. So now I just merged the two layers, N layer and P layer. நம்ம ரெண்டுத்தையும் merge பண்ணிருக்கோம், that's all. So merge பண்ண point நான் என்ன சொல்லியிருக்கேன் அப்படின்னா, that is simply we are calling it as junction. Finish, sir. Fine. So far we understood so many things here. Next, this diode basically will be operated in two regions. Guys, I am telling here, I am not going to cover all the concepts here. I have already told you, I am simply covering the things which are required only to solve the problems. And we are going to cover all the things which are required in the examination point of view through the problems. I will tell you one by one whatever the things that we are learning as a new way, just to make a hint properly and revise it. Apart from that, if you find any new things, no issues. ஏதாச்சும் புதுசாக கற்றுக்கிட்டீங்க அப்படின்னா யூ ஹாவ் டு மேக் அ நோட். அதையும் நீங்கள் நோட் பண்ணி வச்சுக்கிட்டோ ஒவ்வொரு டைமும் ப்ராப்பராக ரிவைஸ் பண்ணிக்கோங்க. தட்ஸ் வாட் ஐ கேன் டூ. ஓகே, ஃபைன் சார், லெட் அஸ் கண்டினியூ. ஸோ திஸ் இஸ் ஜங்ஷன், NP junction diode. So now basically this is called diode. Now you can design it in alternative way also. What is the alternative way? First I have taken N, next I have taken P. Now suppose you people are willing to design PN junction diode. No sir, I don't want NP, I just want PN junction diode. Of course you can do. You can take a positive layer first and then take a negative layer. Now you all know the actual significant meaning of P layer and a negative N layer. P layer means this layer is carrying more and more amount of positive charge carriers. This layer is carrying more and more amount of negative charge. That is the difference between these two. So this is simply called PN junction diode. So we are calling it as PN junction diode. Now with the help of these two diodes, we are going to design our superstar BJT, bipolar junction transistor. But before entering into that part, it doesn't matter whatever the type of the diode that we are going to use. All I wanted to know is the general expression. What general expression we need, sir? Let me tell you. Basically what will be happening here is this N and P layers, after merging them together, they will be producing a transient effect. They will be producing transient effect. Sorry sir, what is this transient effect? In the word நீங்க எங்கேயாச்சும் படிச்சிருக்கீங்களா sir? What is the actual meaning of this transient? You might have read this word in network theory. Network theory there is one separate chapter, sir. Yes, what is that separate chapter? DC transient analysis, AC transient analysis. What we are basically doing there, அங்க ஆக்சுவலா என்ன நடந்துட்டு இருக்கும் அப்படின்னா, in our electrical devices, basically in order to implement the desired performance or desired achievements, whatever the things that you want to do in electrical engineering, there are three supreme passive elements are required for us in order to achieve our desired application. Who are them? The desired elements in our network theory, we might be read about it. First one is called, who is this? Resistor. And second one is called, who is this? Inductor. Third one is called what? Who is this? Capacitor. What happen is, இந்த எலிமெண்ட்ஸ் எல்லாம் வந்து ஒரு சில இடத்துல என்ன பண்ணுவாங்க அப்படின்னா, நாமளே வந்து நம்மளோட இன்டென்ஷன்ல வந்து இந்த எலிமெண்ட்ஸை டிசைன் பண்ணி ஃபிக்ஸ் பண்ணுவோம். ஒரு சில இடத்துல என்ன ஆகும் அப்படின்னா, we are not keeping any coils, any capacitor, but invisible effect. You can see in transmission line, there is a separate chapter is called, separate subtopic is called modeling of transmission line, modeling of short transmission line, modeling of medium transmission line, modeling of long transmission line. So what kind of modeling is there? Why we are designing them separately? Because unfortunately what happened is, after designing the transmission line, people started experiencing the effect of resistor, that is power loss, experiencing the effect of magnetic interference, experiencing the effect of electrostatic interference. Everyone had shocked very first time when they invented this. Sir, I was just started carrying some aluminum transmission line. But what happened is, in that aluminum transmission line, I did not kept any inductor, I did not kept any visual capacitor, I did not kept any resistor. But what happening is, when the moment I am trying to transmit the power from one end to another end, I am facing power loss. Power loss means I square R loss. It is because of the resistor heat effect. And second, we are also started experiencing the effect of magnetic interference. And electrostatic interference, if you keep any communication channel lines near to our transmission line, automatically that communication, the information that we are trying to pass it through the communication channel will get disturbed. So people understood that something is happening invisibly in the transmission line. So the conclusion is, without the effect of resistor, capacitor, inductor, there is no components are existing in this electrical world. So the conclusion is, what happened is, it doesn't matter what type of element that we are designing. Definitely inside that element you can experience the effect of this resistor or inductor or capacitor. Like that, even in PN junction diode also we are experiencing the effect of capacitors. So transient effect automatically will be experienced inside this capacitor. So when the moment they are started carrying the current, they will not accept the changes instantaneously. Slowly, these charges are trying to go from one place to another place. It may be from P to N layer, or it may be from N to P layer, or it may be a forward bias, or it may be a reverse bias. You all know the actual meaning of forward bias and the reverse bias. Of course, I will be telling that in later point. First, we will just cover what are the things that are required in the BJT point of view. So what will be happening is, basically this PN junction diode or NP junction diode, simply we are calling it as diode, will be operated in two regions. One is called forward bias and another one is called reverse bias. Now let us entering into that point. You all know people used to draw like this. If they are talking about forward bias, it's better to draw it in the alternative way. 1 second. So if they are talking about forward bias, what they used to do is, they will be a drawing. You can observe in every textbook. PN junction diode means they will be keeping x and y axis. Forward bias characteristics will be like this. Negative bias characteristics will be like this. Yes, a negative bias இதோட முடிஞ்சிருச்சு. இதை தாண்டி போனீங்க அப்படின்னா diode வந்து damage ஆகிடும். Our PN junction diode will get damaged, not our Zener diode. Zener diode will operate in this region, you all know, right? It can be operated in 3 regions, but our normal power diode can be operated only in 2 regions. This region is called reverse bias region, that is called forward bias region. What is this? This curve is exactly indicate that the current flow through the diode. See, this is voltage versus current. What will be happening here is, in the forward bias I am trying to keep on increasing the voltage. Yes, so when you are at the moment initially from 0, when we are injecting some amount of positive voltage, there is no current flow. If you observe, initial current value is very less, approximately that value is equal to 0. Now when I am trying to keep on increasing the positive voltage, after a particular time period, suddenly this diode will get turned on. Then it start carrying more amount of current. See the drastical increment in the value of current. After that, there is very less amount of voltage is sufficient to carry this much amount of current. That current value is keep on increasing according to the specified rate of the diode. Up to its maximum specification current rating, you can pass that current through the diode. So what will be understanding here is, the nature of the current carried by the diode is exponential. Even in reverse bias also you can observe the same pattern. In reverse bias also, initially reverse current will be 0, 0, 0, 0, 0, 0. There will be slowly increasing and then it gets saturated to the maximum point. If you are trying to push this diode to operate beyond this point, then diode will get damaged, because that is the maximum reverse blocking ability of the diode. It can black up to this percentage only. After that, automatically it will get breakdown. Basically, reverse bias means that state is called blacking state. Diode will be blacking. Sir, is it going to black what? So in reverse bias, there is no current flow. So the value of current is 0. There is no conduction. So if current will be 0 means, see, in reverse bias, the current value is very less. It is in microampere or nanoampere. So almost it will be equal to 0. Microampere means, suppose if I am writing the current value is 1 into 10 power minus 6. How you will be writing this current? 0.0000001 ampere. So this value is approximately equal to 0 ampere only. So we are not considering this effect. This is not a significant value. So current is 0. Current is 0 means according to our basics. So what we can say, current 0 means that is open circuit. Yes or no? So reverse bias is basically acting as a open circuit here. Open circuit means it is blocking voltage here. We know in open circuit you can measure. In open circuit current will become 0 automatically. So there is no point of talking about current. Then what will appear here? If you connect one voltmeter in the open circuit, you can measure the value of voltage. Yes or no? So in reverse bias, it is blocking the voltage up to a certain point. If you are trying to push the diode to operate beyond that point, automatically diode will get damaged. Because that is the maximum blocking ability. Suppose உங்களால் வந்து என்ன பண்ண முடியும் அப்படின்னா, இப்போ நீங்கள் வந்து ஒரு நெருப்பு கட்டி எடுத்து வந்து நம்ம கையில் வைக்கிறாங்க. பேசிக்கலி வாட் வி கேன் டூ, இப்போ நெருப்பு கட்டி கையில் வச்சு ஒரே செகண்டில் நீங்கள் வந்து தூக்கி போட்டீங்க அப்படின்னா எதுவும் ஆகாது. பிகாஸ் அவர் ஸ்கின் இஸ் ஹேவிங் சர்டன் டைம் கான்ஸ்டன்ட். நம்ம பாடி இருக்கு இல்லையா, நம்ம பாடியோட ஸ்கின் வந்து ஒரு டைம் கான்ஸ்டன்ட் இருக்குது. நீங்கள் நெருப்பு எவ்வளோ பெரிய கட்டியாக இருந்தாலும் டக்குன்னு கிட்ட வந்து உடனே, பெரிய கட்டி நம்ம சொல்ல முடியாது, ஒரு ஒரு பர்டிகுலர் சைஸ் எடுத்துகிட்டு வந்து கையில் போட்டு உடனே தூக்கி அடிச்சிட்டாங்க. ஈவன் ஒரு செகண்ட் கூட கிடையாது, அதுக்கு முன்னாடியே வந்து தூக்கி போட்டீங்க அப்படின்னா நத்திங் வில் ஹேப்பன் டு யுவர் ஹேண்ட். பிகாஸ் யுவர் ஸ்கின் இஸ் ஹேவிங் சர்டைன் டெம்பரேச்சர் டைம் கான்ஸ்டன்ட். அதாவது டெம்பரேச்சர் அக்செப்ட், அந்த ஸ்கின் வந்து அக்செப்ட் பண்ணுறதுக்கு ஒரு 1 செகண்ட் இல்லை ஒரு 2 செகண்ட்ஸ் 1.5 செகண்ட் அந்த டைம் இருக்கும். அந்த டைமுக்கு முன்னாடி நீங்கள் நெருப்பை வந்து கிட்ட எடுத்துகிட்டு வந்து தூக்கி போட்டீங்க அப்படின்னா நத்திங் வில் ஹேப்பன் டு அவர் ஹேண்ட். பிகாஸ் தட் டைம் கான்ஸ்டன்ட், அவர் பாடி ஆல்சோ ஹேவிங் டிரான்சியன்ட் எஃபெக்ட். இட் வில் டேக் சர்டைன் டைம் டு அக்செப்ட் தி டெம்பரேச்சர். ரேட்டட் டெம்பரேச்சரை தாண்டி அது போகும்போது ஸ்கின் வந்து என்ன ஆகும், பேர்ன் ஆக ஆரம்பிக்கும். ஸோ லைக் இன் தி சேம் வே யூ கேன் அப்சர்வ் தி எஃபெக்ட் இன் டயோட் ஆல்சோ. ரிவர்ஸ் பயாஸில் அதோட மேக்ஸிமம் பிளாக்கிங் எபிலிட்டி வந்து 100 வோல்டேஜ் அப்படின்னா அந்த 100 வோல்டேஜ் இருக்கும், there will be no issues. அதை தாண்டி நீங்கள் அப்ளை பண்ணும்போது ஆட்டோமேட்டிக்லி லைக் அவர் burn is burning, diode also will get burned or it will get damaged. It will not burn actually, it will get damaged. Okay, so this is the basic property. And one more thing what we understood here is that this diode is basically, it is an exponential effect. It's current, whether it is in forward bias or reverse bias, it doesn't matter. Then how should I express this current? See, what we understood here, diode current is basically exponential current. This exponential current universally written in the form of, see there, we are considering reverse saturation current. Here it is better to write in this way, reverse saturation current. I can write in bracket e power anode to cathode voltage VAK upon eta times of VT minus 1. So this is the generalized formula to express the diode current. Okay, so just remember this. See, this all terms are lies in the power of exponential and then minus 1. I'm writing it clearly. This diode current can be written as reverse saturation current into, in the power of E, in bracket in the power of E. 1 minute guys. Yes, so if you write E in the power of E VAK divided by eta times of VT and then whole exponential term minus 1. So this is the actual expression for current flow through the diode. See that now this is what we understood. Remember it, that is very very important. Fine sir. Suppose now if I am going to design with the help of this diode, now we are going to design some other component that is simply called bipolar junction transistor. So we are entering into our next superstar. Like our diode, this bipolar junction transistor BJT also classified into two types. Exam, sorry, even in semester exams also you might be read this word. So BJT means it can be called it as, we can design NPN transistor or we can also call it as PNP transistor. Yes sir. So one is called NPN transistor, another one is called PNP transistor. Now how can I design this NPN transistor or PNP transistor? With the help of this diode. Basically, இப்போ இதில் பாருங்களேன், NPN transistor அப்படின்னா how many layers are there in NPN transistor? So there are 3 layers. How many layers are there in PNP transistor? There are also 3 layers. But how to design this 3-layer component with the help of 2-layer diode? What we know is, we know our diode will be having only sorry guys, we know our diode will be having only 2 layers. But in order to design the BJT, I need 3 layers. How to bring 3 layers with the help of 2 layers diodes? That's what we are going to learn in the next stage. So we need 3-layer device from a 2-layer device. So first let us take NPN transistor. So NPN transistor means basically how we are going to represent it. So the case number 1. So in order to design the NPN transistor, sorry guys, actually I think I'm not little bit feeling well. Okay. So 1 minute. Yes. See, the NPN transistor, basically how we are representing the universal representation of the NPN transistor. You all know, sir, transistor will be represented like this, sir. Yes, exactly, that is correct. Now, if you observe, how many layers are there? Sorry, how many terminals are there in NPN transistor? Totally three terminals. So this is terminal number 1, this is terminal number 2, this is terminal number 3. Yes, sir. Now, what is the name? NPN transistor. So this is top is going to be N, center is going to be P, bottom is going to be N. NPN transistor. Now see there, P, that is base. We are having base here, right? So this is N, this is N. So this is basically called NPN transistor. Okay, sir. The NPN transistor, the current FD per flow, it will be like in case of diode also we will be having two terminals. One is called anode, another one is called cathode. So the current will be directly flowing from anode to cathode. That is what we are calling it as forward bias. And we all know in the reverse bias, diode will not carry the current, any current ideally, but practically some amount of saturation, that is reverse saturation current will be there. A very less amount of current, approximately that will be equal to 0. If the current is flowing from cathode to anode, we are reversing the direction. That's why that is called a reverse bias. So our intention is we need to carry the current from forward bias, that is anode to cathode. When we are trying to pass the current from anode to cathode, that is called a forward bias. Suppose if any current is tries to go in the opposite direction in the sense from cathode to anode, that is called simply reverse bias. In the same way, basically this NPN transistor will going to be implemented with the help of diodes only. Soon I will let you know. Now, just we wanted to know the direction of NPN transistor. In case of NPN transistor, we are injecting the current from the upper layer and the center layer. From this both layer, we are going to inject the current. From the base, we are going to inject the current. From the top layer also, we are going to inject the current. So this current will come like this. This both will enter together and then they will go out of this transistor through the help of one more layer, that is called bottom layer, layer number 3. This layer number 3 is basically called emitter. Why it is called emitter? So here it is emitting the charge. Okay, that is here in NPN transistor we are trying to pass the current outside. So positive charge carriers are going out. So here it is emitting the positive charge carriers because current is going outside, no? Yes, sir. So how we are representing is, if the current is, see, the top layer is called collector. So it is collecting the, see, current is entering, right? So positive charge carriers are going inside. And then see, in NPN transistor, we will be talking about positive current. In PNP transistor, we will be talking about negative current. Basically, current direction will get reversed. Just do remember like this, such that you can easily remember everything. Okay. Okay, sir. So in NPN transistor, we will be having three terminals. One is called collector, another one is called base, and the last one is called emitter. Now we are collecting the current through the base and the collector, and then it will be passed through the emitter. So now if you apply KCL, closely observe, we are understood that there are three terminals. Yes, sir, there are three terminals. From the upper terminal, we are collecting a current that is called collector current. One more current also being injected through the base, that is called base current. These two currents are together going through the emitter. Now if you apply Kirchhoff current law, according to Kirchhoff current law, at this junction, entering currents are collector current and base current. Algebraic sum of entering current will be equal to algebraic sum of leaving current. Leaving current is emitter current. So in transistor always the emitter current will be the addition of collector current and base current. That's very important. Okay, sir. And one more thing is what I would like to say is this base current always will be in microampere. Approximately this value always will be in micro or milliampere. Most of the cases it will be in microampere only. So what I want to say is this current value is very, very less. Basically, we are using this current in order to control our transistor. BJT transistor is there, na? This BJT transistor is a controlled device. Our diode is uncontrolled device. If you are talking about only diode, which is having anode and cathode, diode is simply called uncontrolled device. Uncontrolled device means you cannot control it from the outside. Sir, what you're trying to mean? What I'm trying to mean is simply we can say. இப்போ நம்ம வந்து we are ஒரு 10th standard வந்து படிச்சுட்டு இருக்கோம் அப்படின்னா சம்திங் நம்மளை யார் கண்ட்ரோல் பண்ணிட்டு இருக்கா? இன் 10th standard in our childhood everybody will be controlling. வெளியில் தெருவில் போகிறாங்க வராங்க, சொந்தக்காரங்க, ஸ்கூலில் டீச்சரு, எவ்ரி ஒன், பேரண்ட்ஸ், எவ்ரி ஒன் வில் பி கண்ட்ரோலிங் எஸ். there are so many controller around us. ஒரு 20 ருபீஸ் 30 ருபீஸ் நம்மகிட்ட கொடுத்தாங்க அப்படின்னாக்கா போயிட்டு வந்ததுக்கப்புறம் வீட்டில் அந்த 30 ருபீஸ்க்கு நம்ம கணக்கு கொடுக்கணும். சார் அப்போ நான் இந்த 10 ருபீஸில் இதை வாங்கினேன், இந்த 10 ருபீஸில் இதை வாங்கினேன். So that is in our childhood stages. That is called controlling effect. Basically what will be happening is they will be giving some money that is called input, and we are going to spend it somewhere, that is called output. In between this what we are doing, we are trying to, we will be controlled consciously we will be controlled by some other components. ஒவ்வொரு காசு நம்ம ஸ்பெண்ட் பண்ணும்போது அப்பாவுக்கு எதை கணக்கு கொடுக்கணும், அம்மாவுக்கு எதை கணக்கு கொடுக்கணும். See, that is one thing. What will be happening is after okay எல்லாத்தையும் படிச்சு முடிச்சு ஜாபுக்கு போனதுக்கு அப்புறம் same thing will be controlled with the help of our mind. We will become more responsible to our family. Suppose if I am learning, let us take my earning is 2 lakhs per month. Just assume I am earning 2 lakhs per month. So what I have to do, I have to spend some amount of money to our family, some amount of money to our brother, to some amount of money to our sister, some amount of money to my wife. Like that I have to our family. So we have to divide the money in this way. How we are dividing? Because more responsibility, that word is called controller here. இது எல்லாத்தையும் நம்ம பண்ணியே ஆகணும். We have a certain kind of emotional bond. So that is called controlling action here. So இந்த கண்ட்ரோல் இல்லைன்னா நம்ம என்ன பண்ணுவோம்? Whenever we are getting 2 lakhs, we will be எந்த வே நமக்கு வேணுமோ அப்படி ரோட்டில் பார்க்கும்போது இப்போ யார் சீங் ஏதாவது பப் பார்க்குறோம் அப்படின்னா பப்பில் போயிட்டு we are spending 20,000 30,000 happily we are drinking and enjoying the party. Then we are again going outside, we are taking the bike, we want wherever we want to drive, we can drive and we can eat anything, any kind of food that we want. That kind of life is what uncontrolled life. The way we are just யாரையுமே நம்ம கேட்க தேவையில்ல, நம்ம மைண்ட் ஆல்சோ இஸ் நாட் going to ask any question, do whatever you want. That kind of device is called uncontrolled device. So in that way we are dividing the uncontrolled and controlled devices here. So here if you take the diode, diode பார்த்தீங்கன்னா ஆனோடு கேத்தோடு மட்டும்தான் இருக்கு. ஆனோடில் நீங்கள் எதை கொடுக்குறீங்களோ லைக் we are getting the salary, we are spending it the whatever the way that we want to do. அந்த மாதிரி ஆனோட் வழியாக கரண்ட் உள்ளே போகும், கேத்தோட் வழியாக வெளியில் போகும். இட் ஜஸ்ட் டயோட் வந்து எந்த வேலை அதை டெலிவரி பண்ண விரும்ப அந்த வேலை ஜஸ்ட் we are letting it to do. But in BJT it's not like that. BJTல என்ன ஆகும்னா கலெக்டர் வழியாக என்ன ஆகணும், let us take collector தான் வந்து we are going to collect from through the collector, we are going to receive the salary. Through the emitter we are going to divide the salary, like this much amount of money is going to will be credited to our family, this much money will be credited to our family, like with our wife, like that some other things. This much amount of money will be credited to our sister family, brother family, everything. So diversification, this controlling could be possible. அப்போ இதெல்லாம் கண்ட்ரோல் பண்ணுறது யாரு? In case of as, it will be our brain. In case of BJT, it is your base. This base current is basically controlled. எப்படி கண்ட்ரோல் பண்ணோம் அப்படின்னா இட்ஸ் அ கைண்ட் ஆஃப் வால்வு. இப்போ வால்வு அப்படின்னா என்ன? இப்போ நம்ம டேப்ல வந்து தண்ணி திறக்கிறோம்ல, தண்ணியை நீங்கள் டேபை வந்து திறக்க we will get more water. Again நீங்கள் க்ளோஸ் பண்ண amount of water is continuously decreasing. It is in the same way. You can just compare this BJT with a tab. So tab is your base. So நீங்கள் டேபை ரொட்டேட் பண்ண என்ன ஆகும் அப்படின்னா வாட்டர் ஃப்ளோ அமௌண்ட் will be keep on increasing. See, from the collector current will be going to the emitter like that. But here basically what happen is it will be injecting some amount of current. இங்கே என்ன இருக்கும் அப்படின்னா இந்த டிவைஸை பொறுத்த வரைக்கும் இந்த கண்ட்ரோலர் அப்படிங்கிறது ஒரு எம்டி பாக்ஸ் மாதிரி, அந்த பாக்ஸில் கரண்ட்டே இருக்காது. ஸோ பேஸ் தான் வந்து என்ன பண்ணும் அப்படின்னா சர்டன் அமௌண்ட் ஆஃப் சார்ஜ் கரண்ட்ஸ் வந்து இன்ஜெக்ட் பண்ணி இந்த ரெண்டு பேருக்கு நடுவில் இருக்க வால்வை வந்து டர்ன் ஆன் பண்ணிவிடும். ஸோ such that they will get the connection. So basically we are controlling the BJT with the help of a valve. That valve is carrying a very small amount of current. So that's why BJT is often called current controlled device. Why we are calling it as current controlled device? Because basically the current carried from the collector to emitter will be controlled with the help of base current only. Base current, often we are talking about base current. Okay, so do remember this. BJT is simply called what? Current controlled device. Understood? Why it is current controlled device? Because we are controlling the current flow from collector to emitter or emitter to collector. It will be reversing also. In PNP transistor we will be talking in the opposite direction. It doesn't matter where we are going, from where we are coming. So between collector and emitter, the current can be fully controlled with the help of base current. That's why it is called a current controlled device. Understood? Yes sir, it is over now. What is our next task? As I told that this value of base current is very less. See, actually in the நம்ம brain மாதிரி தான், brain will going to simply help us consciously spend this much of money here, spend this much of money here. அந்த மாதிரி நம்ம earn பண்ணும்போது ஜஸ்ட் ஒரு இன்ஸ்ட்ரக்ஷன் மட்டும் தான் கொடுக்கும். இதோட ரெஸ்பான்சிபிலிட்டி, இதெல்லாம் நீ பண்ணணும், இதெல்லாம் பண்ணக்கூடாது, அந்த மாதிரி it will be controlling us. So அதை கண்ட்ரோல் பண்றதுக்கு it need very less amount of energy. அந்த எனர்ஜிக்கு ஜஸ்ட் நம்ம கொஞ்சம் நல்லா ஹெல்த்தியாக சாப்பிட்டா போதும், ஹெல்த்தியாக பாடி வச்சுக்கிட்டா போதும். வி நோ நீட் டு, நீங்கள் ஏர்ன் பண்ணுற 2 lakhs மணி வந்து நம்ம பாடிக்காகவே ஹெல்ப் இன்வெஸ்ட் பண்ண வேண்டிய தேவையில்லை. ஸோ பேசிக்கலி வாட் ஐ எம் ட்ரைங் டு மீன் இஸ் தி எனர்ஜி கன்சியூம்டு பை தி பிரைன் இஸ் வெரி லெஸ். லைக் இன் தி சேம் வே தி கண்ட்ரோலர், தி கரண்ட் கேரிடு பை தி கண்ட்ரோலர், தி பேஸ் இஸ் கேரிங் very less amount of current because it's a simple controller. It will going to control the current flow through the collector from emitter. That's why the value of the controller is very less. It don't need much amount of current. It's a small controlling device. It will going to instruct, okay, carry this much of current, don't carry this much of current, like that. So conclusion is, what we understood is emitter current is basically the addition of collector current plus base current only. But unfortunately the value of base current is very less. So we can also say that the emitter current is approximately equal to the value of collector current only. That is the one more case I would like to suggest here to add. So what I am trying to mean is approximately. Don't forget this word, because while solving the problem, in some cases collector current will be known, but there will be not any clue to identify the value of base current. If you are having the clue to calculate the base current, then you can add collector current with the base current. These type of questions also there, these type of questions also there. So in case number 1, they will be giving all type of clue. So where you can deal with the collector current, base current, adding these two, you can calculate the value of emitter current, then you can bring all type of relations. But in some cases only emitter current will be given or collector current will be given. None of other relations will be given to determine the value of base current. So in that case, directly you can say approximately the value of emitter current will be equal to collector current only, sir, because we know the reason why it is. Understood now? Yes. So far we have been discussed about what? NPN transistor. You can apply all these basics to PNP transistor also. But prior to that, I am just trying to expand it a little bit. So I told that this is NPN transistor. NPN transistor means basically it will be carrying 3 layer. But what I told you, how to design this 3 layer with the help of 2 layer diodes. Sir, ஒரு diode 2 layer தான் இருக்கு. ஆனா இங்க எத்தனை லேயர் தேவைப்படுது? In order to design the NPN transistor, I need 3 layers. அப்ப நான் என்ன பண்றது? கண்டிப்பா ஒரு diode இது possible இல்ல. So what people started doing is they have taken 2 diodes. So I am taking 2 diodes. NP diode only, right? So let us take 2 NP diodes. NP. Again they are thinking, okay sir, starting la N வரணும், ending la N வரணும், நடுவுல மட்டும் தான் P வரணும். அப்ப என்ன சார் பண்றது? See, அப்ப இந்த diode வந்து பேசிக்கா நம்ம எப்படி represent பண்ணுவோம்? Anode to cathode. Again, this is also anode to cathode. That is the way of representation. இப்போ நம்ம என்ன பண்ணோம் அப்படின்னா, எனக்கு N to P கனெக்ஷன் வரணும், again N to P கனெக்ஷன் வரணும். அப்பதான் NPN டிரான்சிஸ்டர் டிசைன் பண்ண முடியும். அப்ப இங்க என்ன பண்றது? N வந்து எண்டிங்ல வரணும், P வந்து ஸ்டார்டிங்ல வரணும். இந்த இடத்துல நம்ம ரிவர்ஸ் பண்ணணும் டைரக்ஷன் ஆஃப் தி டயோட். சார் நோ, that's why we are calling it as back to back connection. Diode will be connected in back to back direction in order to design NPN transistor. Now look into this. This is N, this is P, sorry, this is also N, center, this is P, this is also P. See, when both the junctions are carrying same positive charge carriers, then why we are trying to keep it them separately? ரெண்டு பேருமே ஒரே மாதிரி இருக்காங்க, same amount of property they are carrying. So what can we do? Instead of separating them, you can merge them together such that you can treat it as a single layer. That's how we are designing a 4-layer device will be converted into 3-layer device. I am repeating once again. In the center junction, we are having 2 positive charge carriers identical to each other. So they will be merged together. They will be treated as a single P. So finally, it will become a 3-layer. A 4-layer device will be converted into 3-layer device. That's how we are getting NPN transistor. Now what is the meaning? This first layer is carrying majority of negative charge carriers. Second layer is carrying majority of positive charge carriers. Third layer is carrying majority of negative charge carriers. How many junctions are there? Now if you observe them carefully, sir, basically there are 2 junctions. See, between N to P we will have a junction. Between P to N also we will be having one more junction. Okay, now you can decide at any way that you want, right? So later you may be observing the operation and the characteristics of NPN transistor, that things that are later. Okay, just understand this is how we are designing NPN transistor. In the same way you can also design PNP transistor. Same structure, take a strip and then take one more inclined line, take a strip, again vertical strip, inclined line, vertical strip, one horizontal line, merge them all together, we will be getting PNP transistor. But PNP name itself, it's showing that, see, they are dual to each other. Dual means what? We have to reverse them. In order to achieve this, we have to reverse. See, NPN transistor means, see, in place of N, I have to replace P. In place of P, you have to replace N. Again, N place, in place of N, replace P. That is called duality. So if I will replace P by N and N by P, you will be getting PNP transistor. So in that point, what can we do now? We have to reverse the direction of the current also. In case of NPN transistor, current is going from, what we saw, NPN transistor means current is going from collector to emitter, sir. It is in downward direction and current is entering into the base. So in PNP transistor, then what we have to do? We have to reverse the direction of the current. Yes, sir. So everywhere. So in, again, top layer is called collector, undoubtedly. Bottom layer is called emitter, undoubtedly, and the center layer is called base, and we are naming it as, so this is P, this is also P, and this is going to be N. And how can we write down the direction of the current? The direction will be represented through the emitter, current will going to enter, through the base current is going to leave, through the collector also current is going to leave, because they are dual to each other, like PNP and NPN transistor are opposite to each other, right? That is called a duality property. Okay, sir, if I will apply KCL here, then it will not be differ. What I said, for the entire transistor, this property will be remain same. PNP la enna pathinglo, that will be, sorry, NPN la enna pathamo, same for PNP. How it is possible, sir? Let's see. Basically, if you observe, once again there are three layers, three ways are there. Okay, current is entering through emitter, leaving through base and collector. Now if you apply KCL, what you will be getting? I can write emitter current is nothing but, once again, it is the algebraic sum of collector current plus base current only. When the value of base current is very less, then the emitter current can be approximately equal to the value of collector current only. Why? Because this value of base current will be very less. Did you understand? That's all. So that is how we are representing these things. Okay, sir. So 1 minute. Okay, fine. So these things you have to remember, you have to keep it in your mind. So now we understood about NPN transistor and PNP transistor. Okay, sir. Now it's time to talk about other devices. What other devices? Sorry, other operations. So like we have to understand the basic fundamental property of NPN and PNP transistor. So what is this basic fundamental property of NPN transistor and PNP transistor? What we need to learn it here. See, basically in NPN transistor also we saw there are two layers, and in PNP transistor also we saw there are two layers. Yes or no? Yes, sir. Let us take. I am just taking NPN transistor now. In NPN transistor, I told there are three layers. Let me redraw it. There are three layers. Yes, sir. Now center is going to be B. This is going to be collector, and we can call this is emitter, right? How many junctions are there? So I can call collector junction, we can call it as emitter junction. You can represent it in any way that you want to do. Okay, fine, sir. Now in case of NPN transistor, suppose what I am going to do is, if you are injecting positive charge here, what will happen? See, this is NPN transistor, NPN transistor, right? So now there are so many types of operations here, so many types of regions. What is so many types of regions, sir? What are the regions that we are going to consider here? Now suppose if this emitter junction, if you observe between this N to P configuration, we know I only told you that this P is actually, if you break this P properly, there will be 2P. Yes or no? This NPN transistor has been implemented successfully by combining two layers together. Actually, we have taken 4 layers. From the diode, we have taken 4 layers. After that, in the center point, we have merged 2 P layers together. But if we expand, do remember this in your mind. Basically, in the center, always we will be having two P layers. Then only it is very easy to design the diode. Now what happens is, suppose if the collector junction is in forward bias and this emitter junction also is in forward bias, then what will happen? If both people are in forward bias, then the region of operation is called saturation region. Just write down. We need very important. Actually, we are entering into very important zone. I'm not covering entire thing, as I already told you that it's not time to explore all the operation. I'm just covering only the things which are required to solve all the problems. Okay, so I told we are designing about NPN transistor. This P is basically two P's are there inside, just to remember. And I am calling it as collector junction, emitter junction, because it is connected with the emitter. This is connected with the base, and in the center point we are having the base B. Okay, now when collector junction and emitter junction, if both are in forward bias, then the region of operation is simply called saturation region. First conclusion. Suppose the second conclusion, let us make. No sir, if I am taking the emitter junction and the collector junction, emitter junction is in reverse bias, sir, whereas collector junction is in forward bias. What can we do? In this case, you can't do anything. That region is simply called cutoff region. Why? Because when emitter zone is completely turned off, it is not possible to do any operation. Current has to go from collector to emitter. When emitter is blocking, when emitter is doing acting as a reverse bias, it will be acting as a open circuit. When it is acting as a open circuit, it is not possible to carry the current from collector to emitter. So simply that circuit will be turn off device. Turn off means your system is in blocking state. It is blocking the voltage. It is not working now. Cut off. Okay, sir. This is the second stage. Suppose if I am considering, no sir, my junction, emitter junction is in forward bias, but collector junction is reverse bias. What can we do, sir? In this case, we can do, because with the help of emitter, we can design, that is, we can bring the active region. That could be possible. 1 minute. Guys, I made a small mistake. Kindly forgive me. 1 minute. See, that's why we have to do the operation. Emitter junction, collector junction. Basically, here what will happen is, if any one layer is blocked, if it is reverse bias and another one person is in forward bias, we can do some action, because in between these two layers we are having a controller base. With the help of the controller, if one layer is blocked, okay, it is not a problem. Another layer we can actively work with this collector bias, because this base will be helping us to make the current flow. Similarly, suppose if emitter junction will be in forward bias and collector junction is in reverse bias, then also, so it doesn't matter. Okay, sir, no worry about the collector junction. At least your emitter junction is forward bias, right? So base current, with the help of base current, we can do the controlling action. So the complete blocking state will appear when emitter junction and the collector junction both are going under reverse bias. Suppose if emitter junction also in reverse bias, collector junction also in reverse bias, under this situation, with the help of base current also I can't do anything, because already both people are in inactive state. That is called cutoff region. I made a small mistake, kindly forgive me. That's why we should keep our touch always with the subject. And the second thing what will happen is, here, as I already told you, that if emitter junction will be in reverse bias and the collector junction will be in forward bias, right? So just I'm taking emitter in reverse bias, collector. In that case, what kind of region it is called? This is called reverse active region. This is called reverse active region. So we are using this reverse active region. We are not going to use this region anywhere in analog electronics, but it will be used in logic family. Logic family means what? Logic family, it's a small chapter in digital electronics. You might be read that. So there are so many different types of logic family. Basically, we are designing different type of switches. So there we are trying to keep, I don't want to say the device name, just to research and find it. In logic family, in which device? There is only one specific device. There we are going to operate a transistor in reverse active region in order to design a particular desired switching sequence like AND gate, OR gate, NOR gate, NAND gate, XOR, XNORs are there. Na? So in order to bring one particular switching scheme in a logic family, in that logic family there are so many concepts like emitter coupled tri-state logics. There are so many different TTL logics are there now. You might be knowing all these things. So in logic family there is one particular device which will be implemented with the help of reverse active region. Just identify that name. It's an important question. Okay, let me continue. So in analog electronics we are not going to utilize this region anywhere. It is reverse active region. I need active region. Active means emitter bias should be in forward bias. Wherever your emitter junction will be in forward bias, automatically that region will be going to be as a active region. Emitter should be in forward bias and the collector region will going to be in reverse bias. So we can actively operate this device. This is called active region. So now we learn about four regions. One is called saturation region, another one is called active region, then another one is called reverse active region, and the final one is called cutoff region. Just to have a recapture. So we have two terminal, emitter, collector, and the type of the region. That is what we learned now. Just recapture it. If emitter is in forward bias and the collector is in reverse bias, that region is simply called active region. Yes or no? Yes sir. Suppose if emitter is in reverse bias, collector is in forward bias, that region is called reverse active region. I can simply write RA, reverse active. Suppose no sir, both are in forward bias. Both are in forward bias. That region is simply called saturation region. Suppose sir, both are in forward bias, but I have written C. This is called unconsciousness. When both are in forward bias, that is called the saturation region. When both are in reverse bias, then that is called what? Cut-off region. Now, in digital electronics, most of the time, not most, almost 99% of the cases, we will be using two regions. What are those? One is called cutoff region. Cutoff region means off state. Saturation region means on state. So in order to design the switching schemes, we will be operating the transistor in two regions. One is completely both will be in forward bias, another one is completely all will be in reverse bias. On state means basically positive logic, it is 1. There are two type of logic and we will be using only positive logics only. If they will say that they are using negative logic, but that case is very rare. Even I haven't found any kind of questions in the past 25 years with the help of negative logic, right? In switching scheme I'm telling. So negative logic means instead of 1 we will be keeping 0. In on state your value will be 0, in off state value will be 1 in negative logic. Negative logic means just opposite to positive logic. Positive logic means in off state value will be 0, in on state value will be 1. That is how we are designing the switching schemes. So come back to here. In analog electronics, in order to design our switches, we are going to keep our BJT. It is in active region, right? Either it will be in active region or it will be going to the saturation region. So that is what we required here. And we will be talking about cutoff region also, how this device will going to be operated. Basically here you are learning the fundamental basics of the switches. After that you are implementing all those things in digital electronics. That's why always analog and digital will be combined together. Because inside the digital circuits, if we observe, we will be keeping our analog circuits only. That's why I'm talking about this logic switching schemes. They can be implemented with the help of PET, field effect transistors, and we are also designing the switching schemes with the help of transistors, that is BJT, bipolar junction transistor. We can also design all the switching schemes with the help of diodes. We know the basic operation of diodes. So here we are elaborately discussing about these properties. When they are connected to the DC, what will happen? If they are connected to the AC, what will happen? After that, we will be starting doing its applications in digital electronics. Okay. Fine, sir. I hope you understood all these important things. The next most important thing what you have to understand here is the current flowing through the emitter. So how we are going to write down the current flow through the emitter, and what kind of representations that we are going to use in order to write down the current expressions. See, I have written the expression for diode. What is the expression? Just to tell me. I have written the current flow expression. So for the diode, we have written, yes, just to recapture it. For the diode, what is the current that I have written? Diode current will be equal to saturation current. Yes, that is called basically reverse saturation current. Yes or no? Yes, I only written that. That is called reverse saturation current. Now with the help of reverse saturation current, we have written the exponential component of the diode current. So you have to return from there. Again, we have to return the current for the transistor also. See, basically inside the transistor we are trying to keep the same current only, diode current only. So this expression, whatever the expression that we see for the that we saw for the diode current, you can write down the same expression for transistor also. Sir, how should I write this? Nothing. Basically here our major attention is emitter only, active region. We are trying to operate our transistor in active region. I told you that bipolar junction transistor will be operated it in active region. So when we are keeping it in active region, the current flow in active region, what we saw in active region, emitter will be in forward bias and the collector will be in reverse bias. Yes or no? Yes, sir. So it is in reverse bias. So current flow, reverse bias means there will be no any current flow here. Yes. So now what we are going to do is, so the current flow through the emitter is nothing but, emitter means emitter junction. In emitter junction, what we'll be having? We'll be having a diode only. And we know the expression for the current flow through the diode. How will you write? So that is reverse saturation current. Once again I am writing reverse saturation current into e power. In case of diode, we will be having a terminal is called anode to cathode. Yes or no? That's why we are writing it as, that is anode to cathode voltage. But here what will be having? Here we are having a junction. That junction is connected between what? If we take NPN transistor. Yes, can you forgive me? One minute. Okay. So here we'll be having what? So in diode we are having anode to cathode voltage will be eta times of thermal voltage -1. Yes, sir. So in place of anode to cathode voltage, here we will be having our terminals are what? Here the same current that we'll be talking about in between collector to emitter. Actually current is entering in this way, right? So you have to identify the voltage drop across this device. So they will be giving you often the base to emitter voltage will be separately given, and collector to base voltage also separately given. So now we have to identify the voltage drop across the transistor, and then this ideality factor value. This value is going to be 1 basically. Actually what will happen is for this value we will be keeping based on the type of the device that we are using in order to design the diode. இப்போ நம்ம வந்து diode வந்து ரெண்டு விதத்துல டிசைன் பண்ணலாம். One is with the help of silicon, another one is germanium. இப்போ நம்ம ஆக்சுவலாக சிலிக்கான் வச்சு டிசைன் பண்ணுறோம் அப்படின்னா என்ன பண்ணுவாங்க அப்படின்னா, சிலிக்கானுக்கு வந்து they will be writing the value of eta equal to 2 அப்படின்னு சொல்லுவாங்க. ஜெர்மானியம்னால இதோட வேல்யூ வந்து 1ன்னு சொல்லுவாங்க. ஆனால் எக்ஸாம்பிள் வந்து மோஸ்ட்லி வந்து இதை ரெப்ரசென்ட் பண்ண மாட்டாங்க. 95% வந்து இதை ரெப்ரசென்ட் பண்ண மாட்டாங்க. So what people has done is, we have standardly taken this value as 1. By default, in your examination, it doesn't matter whether we are using semiconductor, what type of semiconductor material that we are using here. Is it silicon or germanium? Doesn't matter. I don't want to know about it. If it is represented, if at all, the value of theta equal to 2 அப்படின்னு ரெப்ரசென்ட் பண்ணியிருந்தா மட்டும்தான் நீங்கள் எடுத்துக்கணும். Until otherwise, the value of theta equal to 1 only. Directly you can replace that value by 1. Okay. And sometimes என்ன பண்ண மாட்டாங்க அப்படின்னா, the thermal voltage VT ஓட வேல்யூ வந்து கொடுக்க மாட்டாங்க. சார் அப்போ இது கொடுக்கல அப்படின்னா இது நம்ம எப்படி சார் கால்குலேட் பண்ணுறது? சப்போஸ் இஃப் இட் இஸ் நாட் கிவன், கொடுக்கல அப்படின்னா இதுக்கான டேட்டா கொடுத்துருப்பாங்க, கேடி பை கியூ அப்படின்னு சொல்லியிருப்பாங்க. கேவோட வேல்யூ தட் இஸ் கால்டு போல்ட்மேன் கான்ஸ்டன்ட். See, this is also very rare only. Thermal voltage it will be approximately equal to 25 millivolt. In some cases, in the examination, they will be giving you 26 millivolt. If it is not given, you can take 25. If it is question itself, if they will be giving 26, you can take the 26 also. No issue. Okay. So K is called Boltzmann constant. That constant value will be given. And T is called a temperature in Kelvin. That will also be given. Q is the charge of 1. That is the value of charge of a 1 electron. We can say that is charge of a 1 electron. So after giving all these values, you can easily identify the value of Vt also. Okay, so this is how we are calculating the emitter current. Just do remember this. I will be replacing this by base emitter voltages while solving the problems. Okay, how we are substituting that value, because if I am showing it through the problem, you will be clearly understanding. Okay, don't be bothered about it. So just be patient for very few time. So far what we understood the basic properties of transistor, we understood the basics, region, types of our region, everything we understood, right? Now, if a transistor la pathinga appadina, I would like to write some more things. See, collector current IC equal to indha mari eludhirupanga beta times of IB, sir. From this relation, what we can say is, we know in transistor emitter current will be equal to collector current plus base current. இந்த மாதிரி கொண்டு வருவாங்க. Next step from here, just now I wrote that collector current can be replaced by beta plus IB. So if I will write beta plus IB plus IB, from this I can take IB outside. If I will take IB outside, this can be written as 1 plus beta equal to emitter current. See the only factor. What is the difference between collector current and emitter current now? Just observe the difference. In case of collector current, we are having beta. In case of emitter current, we are having 1 plus beta. You know, this value of beta is very, very large. This value is very, very large. So since the beta value is very, very large, then what we can say, when beta value is very, very large, then 1 plus beta is approximately equal to beta only. Yes or no? So what I can replace? I can ignore this effect of 1. If you are ignoring the effect of 1, then I can say approximately this value equal to IB into beta only. So IC also beta into IB only. IE also beta into IB only. So that's why we are approximately saying IC and IB both are equal. I hope many of you, majority of you people know this relation. But if you focus the transistor, so current gain on the calculate பண்ணும்போது, basically what is this beta, sir? This beta is called current gain only. See, you can simply define this. Let me say how I have written here. Collector current IC can be written as beta times of IB. Yes, sir. So from this, even you can take emitter current also. Emitter current can be written as 1 plus beta times of IB. Sir, always try to go with the exact values. I am telling that, I clearly told that in the examination, if there will be no any clue to identify the value of base current clearly, in that case you can approximately equate the value of collector current to emitter current. Otherwise, you have to solve step by step. Separately solve. Keep 1 plus beta, separately calculate the value of emitter current. Keep beta, calculate the value of collector current, because sometimes they will be giving you decimal, fractional values in the option. In that case, they will be giving you all clues to identify the value of collector current, emitter current separately. Then only you will be getting the accurate answer. Okay, so don't do the approximation when all the data is given in the question. No sir, none of the data is given, only collector current is given. There will be no any clue to identify the value of base current. In that case, you can just equate the collector current with the emitter current. Okay, I hope you people are understanding this, what I am trying to conclude. Okay sir, every one of us know this relation very well. So let us, I told you this is called current gain. Current gain means that is the ratio between two current. Is it true or not? Just to pass the base current to the right side, sorry, to the left hand side. Now see the ratio between collector current and base current is simply called current gain factor here. You all know that we are also having one more current gain. Slowly, I will be bringing all the relations one by one. Okay, sir. Now, let us deeply keep our attention with the collector current first. Even the collector current வந்து நம்ம வந்து deeper zoom பண்ணி பார்த்தோம் அப்படின்னா, this layer, this collector zone will be carrying two current 1 and current 2. கலெக்டர் கரண்ட் மட்டும் தனியாக வந்து அந்த டயோடுக்குள்ளே வந்து ஜூம் பண்ணி பார்க்குறாங்க. ஜூம் பண்ணி பார்க்கும்போது தே ஆர் அப்சர்விங் டூ கரண்ட்ஸ். ஜஸ்ட் ரிமெம்பர் லைக் திஸ். என்ன சார் டூ கரண்ட் அதுக்குள்ளே தனியாக போயிட்டுருக்கா? எஸ். இந்த கலெக்டர் கரண்ட்டை வேறு எப்படி நம்ம எழுதலாம் அப்படின்னா, ஸோ வி ஆர் கோயிங் டு கன்சிடர் டூ திங்ஸ். ஒன் இஸ் ரிவர்ஸ் சேச்சுரேஷன் கரண்ட். One is current through the transistor வழியா போயிட்டு இருக்க reverse saturation current. Okay sir. And plus another one is that is cutoff current also we can call. So this current is often written as ICO. We can also write like this. Okay. And another one is majority carrier current. Majority carrier collector current we can write. So this majority carrier current means you know that in collector region you can observe two type of current now. One is collector is majorly carrying some current, அது வழியா ஆக்சுவலா போற current, plus we are also observing one more current that is called cutoff region ல நமக்கு கிடைக்கிற current, that is reverse saturation current. We often call it as reverse saturation current. Okay sir, we understood this. So basically this is called total collector current. I am repeating one more time. கலெக்டரை வந்து நல்லா ஜூம் பண்ணி பார்த்தப்ப கலெக்டரில் வந்து ரெண்டு கரண்ட் கிடைச்சது. ஒன்று கலெக்டர் வழியாக ஆக்சுவலாக போயிட்டு இருக்க கரண்ட்டு, இது கூட இன்னொன்று வந்து ICO அப்படின்னு இன்னொரு கரண்ட்டும் கிடைக்குது. தட் இஸ் வாட் ஐ எம் ட்ரைங் டு மீன் ஹியர். ஓகே சார். நவ் வி நோ பேசிக்கலி ஆக்சுவல் கலெக்டர் கரண்ட் அப்படின்னா IC. அதை நம்ம பார்த்தோம் இல்லையா, IC ஈக்குவல் டு பீட்டா டைம்ஸ் ஆஃப் IB அப்படின்னு நம்ம பார்த்தோம். கரெக்டா? எஸ் சார், தட் இஸ் ட்ரூ. அண்ட் ஹியர் ஐ எம் ட்ரைங் டு இன்ட்ரடியூஸ் ஒன் மோர் ஃபேக்டர் ஆல்சோ. ஸோ அப்போ இது நம்ம என்ன பண்ணிக்கலாம் அப்படின்னா, பேசிக்கலி வி ஹவ் ரிட்டன் திஸ் கரண்ட் இன் டூ வே. ஸோ இது நம்ம ஃபஸ்ட்டு என்ன பண்ணிக்கலாம் அப்படின்னா, திஸ் கரண்ட் கேன் ஆல்சோ பி ரிட்டன் பீட்டா டைம்ஸ் ஆஃப் IB plus reverse saturation current. Okay sir, this is one way. This is the total collector current. The alternative way to write down this current is total current. Collector current can also be written in terms of emitter current. How should I write this sir? You might have read these things. IC equal to alpha times of IE. சரி, என்ன சார் இவ்வளோ நேரமாக வந்து கலெக்டர் கரண்ட் வந்து அப்ராக்சிமேட்லி ஈக்குவல் டு எமிட்டர் கரண்ட்னு தானே சொன்னேன். யூ ஹாவ் டு observe that word. I wrote collector current is approximately equal to emitter current. Then what is the exact relation? It is exactly equal to what? It is exactly equal to emitter alpha times of emitter current. So from this I can say how you will write the alpha equal to collector current upon emitter current. That is the alternative relation. We can write like this. Okay sir, that is the alternative way of writing the collector current. Okay, that is fine, right? Now what we can do is, so we can substitute this value into this expression, where here also you can substitute this. So the total collector current can be written as, from this, IC equal to what? Alpha times of IE plus ICO. That is the alternative way of writing the collector current. Okay, I hope now you people are understanding what we are trying to mean it here. Okay sir. I'm really very sorry. Okay, now you might be brought this relation when you are comparing this collector current with the emitter current. You know the relation between alpha and beta. Alpha can be written as beta by 1 plus beta. Guys, I'm skipping some 3 to 4 steps derivations because that is not that much mandatory here. So we have to solve so many problems. The relation between beta is what? Beta and alpha. Beta can be written as alpha divided by 1 minus alpha, whereas alpha can be written as beta by 1 plus beta. So now you can also write down, if you replace this alpha by beta, this can be written as what? Beta by 1 plus beta. Or else you can also replace this beta by alpha. If you replace this beta by alpha, then it will become alpha divided by 1 minus alpha. Yes or no? So there are so many ways to write down these expressions. So it is up to you hereafter. Based on the, according to the given data in your examination, you can go up with the data. Just to remember all these relations in the examinations. Whatever the way that they are trying to give the expression, just to substitute it. Okay, fine sir. So now finally you understood the total collector current. Okay sir. In the same way, so one minute guys. Okay, so in the same way, in terms of completely alpha, how should I write the collector current, total collector current? Let me write. And in terms of complete beta, how should I write the collector current, sir? Right? So completely only in terms of alpha. So first I am writing the total collector current in terms of alpha. This can be written as, it will be given all the data in your examination, they will be giving you the data just to follow it up. Okay, so this can be written as alpha times of I beta, divided by, just now I have written this relation, plus saturation current. So we can write this one. Similarly, if you can also write down this for emitter current. Emitter current will become base current divided by 1 minus alpha plus saturation current upon same value will become 1 minus alpha. So this is how we are writing the relation for emitter and collector current only in terms of alpha. Suppose if you want to write it in terms of beta, then what we can write is collector current will become, basically it will become beta times of I into beta. That is most important relation that will be often asked in your examination. 1 plus beta times of reverse saturation current. That's all. Just do remember this, because in the examination most of the time the question is repeatedly asked only with the help of this relation. They will be giving you reverse saturation current and base current will be given, beta will be given. Simply they will be giving only 2-3 lines will be there and everything will be given. You will be asked to find out the collector current. What you people are doing is directly multiplying these two and substituting the answer, not considering this value. So you will be getting the wrong answer. So remember this formula. So that is most important formula. Okay, when this data will be separately given, this is the way you have to express the value of collector current. Okay, I hope you all understand what I am trying to mean it here. Okay, sir. So next, you have to remember some of the characteristics of the transistor. So let us recapture it. I'm just drawing it and you have to remember it. Okay. So when we are entering into BJT, there are different regions and its corresponding characteristics. So we'll be calling it as common base characteristics. In common base, input and output characteristics. Again, if you go common emitter, input and output characteristics. So the most important region is common emitter region for our transistor. So if you take the common emitter region, common emitter means what? Input will be given through the base and output will be taken from the collector. So emitter. So emitter is going to be common here, right? So between input and output. Okay, sir. So when we are taking common emitter characteristics, right? So emitter is going to be a common region, input is going to be the base and the collector is going to be our output. Okay, sir. Now, first thing in the examination, what they will be asking is input characteristics. They will be talking about input characteristics. This actually question on the input characteristics. Let me tell you first what is the input parameter and what is the output parameter. In case of common emitter, we will be having three terminal: collector, base, emitter. When emitter is going to be common, then collector is your when emitter is going to be common, then base is your input and collector is your output. That's all. Nothing else to discuss here. So from this I can say, when input is base, then through the base, whatever the voltage that we are giving. So base to emitter voltage, emitter is common, right? So base to emitter voltage is going to be your input voltage and the base current is going to be your input current. Similarly, if you take the output, again, so collector voltage is going to be our output. Collector to emitter is common terminal representation, right? So between base to emitter, collector to emitter, and output current is going to be your collector current. This is input versus output. Now when we are traveling along with the input characteristics, now suppose if we are taking, I am just taking x and y axis values here. Just remember it. Suppose if I am fixing the value of voltage, that is collector to base to emitter voltage in the x-axis and base current in the y-axis, how its characteristics will be appearing here. Let us take, initially current will be 0. Question la enna kodupanga appadina, they will be giving you various values. Various values na enna appadina, initially collector to emitter voltage வந்து fix பண்ணிடுவாங்க. We are talking about input, right? So output will become fixed. இப்போ collector to emitter voltage வந்து என்ன பண்ணுவாங்க அப்படின்னா, examination they will be giving you, if the value of collector to emitter voltage, initially the value of collector to emitter voltage is 1. Suppose if the value of collector to emitter voltage is increased to 2, what will happen? How its characteristics will be represented? Or if I am decreasing the value of the voltage from 2 to 1, what will happen? So basically it is similar to diode only. If you draw the ideal characteristics, it will be like this. You know how these characteristics will be, but I will be telling you. Listen. So what will be happening here is, at each and every time when we are trying to fix the collector to emitter voltage, suppose in case number 1, I am keeping the value of the collector to emitter voltage is 1 voltage. Then what will happen is, this can be going to be your cutoff region. Sir, it is similar to diode. In diode, what we'll be doing? We are drawing the characteristics like this only. Just observe. Nothing is, it is diode only. Inside the transistor, we will be keeping diode only. So it will be resembling that character only. So similarly, again, if you go, okay, sir, if I am increasing the value of collector to emitter voltage, then this region of this cutoff voltage also will increase, and its value also will increase. See there, the turn on time will take, it will take much more time, then it will turn on through this way. So this will become 2 voltage, we can say. Suppose if I am again increasing it to 4 voltage, then what will happen? Again, this will go to 4 voltage. That is the again cutoff voltage will be increasing. It will take few more seconds to turn on. So what will be understanding here? Just remember it. So base voltage to base to emitter voltage. Suppose sometimes what will happen is, in the examination, they will be giving you, they will keep the current in x-axis, they will keep the voltage in y-axis. We have habituated to keep the voltage in x-axis and the current in y-axis. That's why waveform became like this. Suppose if we reversed this, then how it will be look like? This waveform will be like this. Yes or no? So just observe carefully whether which term they are keeping in which axis. It doesn't matter where they are keeping. So you should know how to draw it. That's very important. Okay, sir, this is input characteristics. Now let us keep our attention with the output characteristics also. So if you go ahead with the output characteristics, it is very important to know about the to keep it in 3 regions, because in output our transistor can be operated in 3 regions. I told you, right? Do you remember what I told you? We have been discussed about 4 region. One is saturation region. Yes, sir. Another one is cutoff region. Yes, sir. Another one is active region. But I haven't talked about reverse active region. Why, sir? I told you we are not going to use it here. Then where we are going to use it? This application you can observe in logic family. I told you only in specific one circuit you can see this. Try to observe in which circuit we are applying it. Okay, it's your responsibility to bring it answer for this. Okay, sir. Drop your answer in the telegram somewhere, in even in comment section also you can keep. I will be happy if I will see your answer. Okay, fine, sir. So let us continue to do this. So saturation region we observe, cutoff, okay, active region, everything is fine, sir. Now when we are talking about the output characteristics, 1 minute guys. Yeah, if you want to discuss about output characteristics, as usual, you can keep your voltage in x-axis and the current in y-axis. That will be much easy for us. So I am keeping once again voltage. Output characteristics means it between collector to emitter voltage and collector current. They are all called our output parameter. So here then what will happen? Current is in y-axis, voltage is in x-axis. So in output, suppose initially I am going to give the input current as 0 base current. Let us start from 0 base current. When the current is 0, then what will happen? Whether your transistor will turn on or not. I am just asking. Just tell me your answer. Drop your answer in the comment section. I am just asking you, if the base current is 0, whether the transistor will turn on or not. What can be your expected answer? Sir, when current is 0, transistor will not turn on. Why? I told you, transistor is called current controlled device. Yes or no? Yes, sir. When base current is acting as a controller, if that terminal is not there, if that current value is 0, it clearly indicates that the transistor will be in off state. It is in off state. It will not turn on. Why? Why? Because you told that current will be 0. Yes, you are correct. It is turn off. So off state means that is called what? In this region, which is called off state, cutoff region. Yes or no? Both are in reverse bias. So we can say, sir, both transistor will be in reverse bias and it will be in cutoff region. Why? Because you told that the base current will be 0. When base current will be 0, there will be no controlling action. So simply what we can do is, okay, sir, you can apply whatever the amount of voltage that you want. You can apply enormous amount of voltage also, but you can't find the current flow through the collector. It is the output terminal. So, but what you can observe is very less amount of leakage current. A very less amount of current will be flowing here. So whenever you are observing, sir, I am continuously increasing voltage, sir, but I am not able to observe the current, sir. What do you have to say? How can you observe the current, buddy? There will be no current through the base. They fixed that the base current is zero. Without base current, how will you control this? There will be no controlling action. This device will become useless. First go and give some current through the base. That can be your expected answer. Yes, sir. So I can say this region is basically called cutoff region, where both the transistors will be in reverse bias. Sorry, not transistor, both diodes, both junction. Junction means what? Emitter to base junction, collector to base junction. Both junction will be in reverse bias. The diodes which are fixed in this both region will be in reverse bias. Correct? Yes, sir. Now slowly what I am going to do is, I told this region of range of current base current always will be in microampere, sir. It is a small responsible, like our brain. Our brain is more sensitive, right? It is having the responsibility to do something for our service to our family. So it is the controller for us. So in the same way, base current also will be the controller for our transistor. Okay, let me keep some 0.5 microampere. Slowly we will be increasing it. Okay, sir. Now, okay, you can 0.5 is very less. Let us take some 3 microampere. Okay. Anyway, I'm injecting some current. I'm telling that now I'm injecting the current. Now what will happen? Happily you can say, okay, if you are injecting the current, then I will be very happy. You can immediately start, yeah, your transistor initially will be in saturation region, then slowly it will be entering into active region. I will be very happy, right? So this zone will become active. Let us break it actually, right? This is called active region now. I think we don't have sufficient space. Let me do it somewhere here. Because that is a little bit important one, common emitter. Often it will be asked in many exams. First understand this, then other things just you can, it will not go down, it will be, sorry guys, it's disturbing me. Yes, so it will be like this. So this region is basically called cutoff region. You can simply fix when base current will be 0, device will be in cutoff region only. You know the answer why it is. Now I am slowly going to keep it in microampere. I am increasing the current. If you increase the current, then voltage also will be increasing. Fine, sir. It will be in increasing zone only. This is called active region. So here we are fixing microampere current, microampere only. The value of current will be in microampere. That is base current. How to written is properly. Base current will be equal to, you can keep some 3 microampere. Fine, sir. Suppose again I am increasing the base current into 5 ampere. Then what will happen? So if you are again increasing, I will be very happy. Then my curve is slowly tilting. It will go in this way. We are trying to improve its character as much as possible. Now it is going like this. Yes, sir. Again further. So here let me keep some 5 ampere. Now I am going to keep it some 8 ampere. Then what will happen? Further it will increase. Yes, sir. So if you want to keep your device in active mode, then it is very important to keep as maximum base current as possible, such that device your device will be in highly active region. Now let us break these regions into 3 zones. So the area that I am covering here. So here this is only area, right? So let me margin. This is called the safe operating area or linear operating zone. Your device will be in linear zone. If you observe, almost this device will be a linear line. This line will be, see, and the strip line will be like this. Almost it will be like this only. So this region is called, if you observe a ramp line, that is called a linear line. So it is keep on linearly increasing with respect to what? X-axis. So that is called active region. That's why this region is also called a linear region, because in active region your transistor characteristics will be linear. Linear means what? With respect to x-axis. If there is any changes in x-axis, immediately in y-axis also the changes will be reflected and it will be linearly increasing like this. So that's why this active region is also called linear region. So I can call this entire zone is called linear or active region, just to remember it. Okay, sir. Fine. Now, if you observe, this one more zone is there, na? Cutoff region. Already I kept that. So let us enter into that point. Now, this region, the second region is called Sorry guys, yes. So this region we can call it as almost, this region is called cutoff region. I can call it as cutoff region. Cutoff region means what? Both the diodes are will be in reverse bias. Whereas active region is what, sir? In active region, emitter junction will be in forward bias, collector junction will be in reverse bias. That is called active region. Okay, do remember this. Okay, sir. I told you we will be keeping our attention to the three region. What are those? One is cutoff region, second one is active region, third one is reverse active region. Yes, correct only, no? No, sir. Not reverse active, sir. You said what? Saturation region. Yes, because reverse active, we are not going to keep our devices in reverse active. That is opposite to our operation actually. Okay, sir. So then we are keeping our attention with the saturation region. Then which zone is called a saturation region? This region. Here only your device will be saturated. So this region is simply called saturated region. You have to observe the operation in order to understand it clearly, but I told you we are not having that much things to do. Just to compare and remember everything. Okay, fine, sir. So basically we understood that our transistor can be operated in three regions. I have clearly explained that in saturation region basically what will be happening is both devices will be in forward bias. In saturation region both the diodes will be in forward bias. You have to be, sir, it's really amazing device because see ரெண்டு டயோடுமே ஃபார்வர்டில் இருந்தால் தான் நம்ம என்ன யோசிப்போம், இட் இஸ் குட் சார், ரெண்டுமே ஃபார்வர்டில் இருக்குது சார், we can operate it in active zone. But you forget to remember one more thing, அங்கே டயோட்ஸ் வந்து பேக் டு பேக் கனெக்ஷனில் இருக்குது. They are not connected like this. If they are connected in this way, then it is very good to observe both are in forward bias. See, both are in opposite direction. One person will be like this, another one person will be like this. In that case, one case will be our ஒரு diode forward bias ல இருந்து இன்னொரு diode வந்து reverse bias ல வரும்போது we will be getting our desired achievement. When both are in forward bias, it will become what? Both are opposing each other. So the current carried by them will be like this. One will be carrying current like this, another one will be carrying the current like this. Is it our desired region here? No, sir. But device will turn on. Obviously, definitely your device will turn on. So here what is our achievement is, my achievement is obviously linear region only. So here our main agenda is in transistor, our entire focus will be with the current only. Okay, in case of bipolar junction transistor, not in every transistor. But if you enter into MOSFET, your attention will be with the voltage. That's why your FET is often called voltage control device. You all know that, right? Bipolar junction is basically controlled with the help of current. But whereas MOSFET will be controlled with the help of voltage, a driving force. Current means our blood, our brain. You can take like this. You can treat you as a BJT. Whereas voltage means our childhood age. Voltage na our father. He is forcing us to do this. Don't do this. You have to. If you want to live happy life, you should not avoid. You have to avoid this. They are giving the guidance continuously to us, right? So we will be controlled by some external force that we can treat MOSFET. So our childhood age. So we had acted as a MOSFET. We were controlled by some other external mechanism. Now our internal blood, our internal brain sequence, when blood flow is good, your brain will be active. You will be more and more sensible, more and more responsible to your atmosphere. You will be conscious, right? So BJT means our present situation. Now we are earning, we are having more conscious, we are doing something, at least we are going to do something. So we are taking our responsibility, at least going to, right? So this is called BJT. So BJT means our living age currently, that is our present age, that is what we are going to do now. So our childhood age you can consider as MOSFET. So MOSFET basically controlled with the help of external voltage. That's why it is called voltage controlled device. Whereas BJT means internal blood, our brain will going to control. That is called, blood is like streaming. It is going from one place to another place, right? So that is simply called electron flow. That is called current. So BJT is simply called a current control device. MOSFET is FET, field effect transistor. It doesn't matter, it is MOS or NP, it doesn't matter. So field effect transistors are simply called voltage controlled device. Just to remember it, right? Very important question. Fine, sir. I hope you understood everything. But remember one more thing. I was talking about this characteristics. I was generally defining it for bipolar junction transistor. For the field effect transistor, this effect will be differ. Why sir? Because field effect transistor is voltage control device. Na? Here I am doing this controlling action with the help of current. So you can't compare this one with that one. But I can say it will be in reverse. Reverse means, sorry sir, I don't understand. Reverse means here we are trying to operate our device in which region? Now உங்ககிட்ட டோட்டலா 3 regions சொல்லி கொடுத்தாங்க, saturation, cutoff, linear. Now tell me, so எந்த regionல வந்து நம்ம transistor operate பண்றோம்? We need linear performance. We achieved that linear performance in active region. So what we understood here is basically bipolar junction transistor must be operated in active region. Linear region is the desired achievement that we want. So bipolar junction transistor will be desired region where it will be operated is linear region, or we can call it as active region. Understood? But in MOSFET that case will be reversed. There you can observe the desired achievements. MOSFET la namakku thevayana characteristics enga kedaikum appadina, where sir it is in saturation region. So in MOSFET our region, we will be keeping our attention with the saturation only. So you do remember only one thing, bipolar junction transistor, you know everything. I taught why it is in cutoff, how it is in active, everything. So just keep everything in your mind. In MOSFET automatically these things will help you to get reverse operation. அது எப்படி ஆப்ரேட் ஆகுதுன்றது we will be keeping your attention there. Okay. Now I am giving you one more suggestion. I have drawn the characteristics of only common emitter because I just wanted to cover these 3 points, active, cutoff, and other things. So I am just keep asking you to understand the input and output characteristics of common base and common collector. Okay, because in sometimes what will be happening, don't do too many things, just observe input output characteristics of common base, input output characteristics of collector, common collector. If you put it in internet, you can find there are so many resources, electrical for you, like India Books, there are so many things. Just you can refer anything, just observe how they are happening and go through that article once, such that you'll be getting more and more idea. My sincere suggestion is don't blindly follow only one author, one teacher. Okay, whatever you want to learn, try to put some effort to learn some things from outside also. He is the good student. Okay, so it is better to learn something from external also. I told you why we have to do in this way. Many people are telling that I am covering 100%, you don't need to do study anything beyond this, such that you will become a master. Okay, when they are telling like that, you will be motivated. Ah, sir, on the super nadata poraru, he is going to be the god. So you will be fixing that. Sir, appo fulla cover pannidavaru. Sir solradha namakku mantram. So you will be starting repeating that mantra everywhere. So what happens is finally when you are facing new questions, automatically, oh my god, why sir did not teach us? So it will be unknowingly happen sometimes, unconsciously. So that's why you have to practice more new questions. But when you are seeing something new, mostly we will be covering everything, but some portion we will be leaving. Unfortunately or fortunate, something will happen. So it's always better to learn it from outside resources also, such that you will be engaged with more and more knowledge. It will be helping you to understand the subject in more better way. In somewhere what will happen is நம்ம நடத்துறத விட நீங்க படிக்கிற விஷயங்கள் வந்து இன்னும் உங்களுக்கு தெளிவா புரியறதுக்கு ஹெல்ப் பண்ணும், because already you understand something here. Again when you are going through it somewhere with some other concept, that will be helping you to understand the subject more and more, right? So it is always better to learn it with using multiple resources, remember it. Okay sir, fine. So my suggestion is just to learn common base characteristics and common collector input and output characteristics, that's all. ஸோ ஆக்சுவலாக டிரான்சிஸ்டரில் என்ன பண்ணுவாங்க அப்படின்னா 3 டெர்மினலில் ஒரு டெர்மினல் வந்து காமனாக ஃபிக்ஸ் பண்ணிடுவாங்க, ரிமைனிங் 2 டெர்மினலில் வந்து ஒரு டெர்மினல் இன்புட்டாகவும் இன்னொரு டெர்மினல் வந்து அவுட்புட்டாகவும் ஃபிக்ஸ் பண்ணிப்பாங்க. தட்ஸ் ஆல். பிகாஸ் நமக்கு 3 டெர்மினல்ஸ் இருக்கு இல்லையா, அப்போ 3 டெர்மினலில் ஒரு டெர்மினல் காமன் அப்படின்னா மீனிங் என்ன அப்படின்னா பேசிக்கலி இட் வில் பி காமன் ஃபார் போத் இன்புட் அண்ட் அவுட்புட். That's why I have written the voltage like this: base to emitter, collector to emitter. Emitter is common terminal, so it will be acting as a neutral point between both input and output. That's why we are always saying that word. Voltage பத்தி எழுதும்போது எந்த டெர்மினல் காமனா யூஸ் பண்றீங்களோ அந்த டெர்மினலோட வோல்டேஜ் வந்து இங்க செகண்ட்ல வந்துரும், this place. Okay, just remember these things. Okay sir, I hope you all understood everything that is required. இப்போ derivation point of view, there are something we need to verify. நீங்க ப்ராப்ளம் சால்வ் பண்ணும்போது என்ன பண்ணணும் அப்படின்னா, people used to give something. Sir, some things I'm just recapturing here. While solving the problem, I will be bringing other things. Okay, one minute. It is stucking. Yes. How to identify the region of operation? That is one more thing that we are out. What is this region of operation? Whether your transistor will be in cutoff region or your transistor will be in active region. I told we are going to keep our attention with the three region: cutoff region, active region, and or your transistor will be in saturation region. Sir, இது எப்படி சார் ஐடென்டிஃபை பண்றது? கட் ஆஃபை பார்த்த உடனே உங்களுக்கு ஞாபகம் வந்திருக்கணும் சார், கட் ஆஃப் அப்படின்னா பேஸ் கரண்ட் ஜீரோ, அவ்வளோதான் முடிஞ்சு. So when base current is zero, you can simply say transistor off state, sir. Don't do anything, just leave it. Finish. Suppose when your transistor will be in active or saturation region, நீங்க நிறைய क्वेश्चन பார்த்திருக்கலாம். Transistor active region ல இருக்கா, saturation ல இருக்கா, active ல இருக்கா, saturation ல இருக்கா, இல்ல cut off ல இருக்கா. This kind of question will be often repeated in your examination. There are so many examples, right? You might have observed these things. Sir, how should I identify these things? For that, nothing is there. You have to assume transistor வந்து ஏதாச்சும் ஒரு ரீஜன்ல இருக்க மாதிரி நீங்களா அசியூம் பண்ணிக்கணும். We don't know in which region our transistor will be. Yes sir, then what can we do? Then assume that your transistor will be in active region, or assume that your transistor will be in saturation region. Then you can proceed further. Sir, suppose if you are assuming that the transistor will be in active region, நீங்க சும்மா அசியூம் பண்ணிக்கிறீங்க டிரான்சிஸ்டர் வந்து ஆக்டிவ் ரீஜன்ல தான் ஆப்ரேட் ஆகுது அப்படின்ட்டு நம்ம அசியூம் பண்ணிட்டு, ஆக்டிவ் ரீஜன் அப்படின்னா லீனியர் ரீஜன், நார்மலா நம்ம ஆப்ரேஷன் பண்ற மாதிரி கேசிஎல் போடுறீங்க, கேவிஎல் போடுறீங்க, யூ நோ எவ்ரிதிங், தட் இஸ் யூ நோ ஐசி ஈக்குவல் டு 1 minute, IC equal to beta times of IB, and IC also equal to alpha times of IE. You know all the relations, right? 1 minute. If you are writing some other KVL equation, KCL equation, right? Mostly என்ன பண்ணுவோம் அப்படின்னா நம்ம Kirchhoff voltage law யூஸ் பண்ணி டிரான்சிஸ்டருக்கு ஈக்குவேஷன் எழுதுவோம். I will be teaching you how to do that, right? So இதை நீங்கள் கால்குலேட் பண்ணி முடிச்சதுக்கு அப்புறம் ஃபர்ஸ்ட் ஸ்டெப் வாட் யூ ஹவ் டு டூ இஸ், சார் இந்த கால்குலேஷன்ல டிரான்சிஸ்டர் வந்து ஆக்டிவ் ரீஜன்ல இருக்கிறத அசியூம் பண்ணிக்கிட்டு ஜஸ்ட் எஸ்டிமேட் தி வேல்யூ ஆஃப் கலெக்டர் டு எமிட்டர் வோல்டேஜ் கால்குலேட் பண்ணுங்க. கால்குலேட் பண்ணதுக்கு அப்புறம் என்ன பண்ணணும் அப்படின்னா, யூ ஹாவ் டு கம்பேர் இன் டிரான்சிஸ்டர். பேசிக்கலி what will happen is they will be giving you the value of collector voltage, VCC அப்படின்னு சொல்லுவாங்க, right? That is collector reference voltage. Okay sir. So இந்த VCC value இங்க இருக்கும், transistor இங்க இருக்கும். So this is collector to emitter voltage. This is collector to emitter voltage. Okay sir. Here the value of collector to emitter voltage in saturation region is less than or equal to 0.2 voltage. Mostly it will be 0.2 voltage only. Right, so the collector to emitter saturation voltage will be 0.2. You can fix this value is 0.2. Okay sir. அப்ப நான் saturation voltage வந்து நான் என்ன பண்றேன்னா 0.2 ன்னு ஃபிக்ஸ் பண்ணிட்டேன். இப்போ collector to emitter voltage வந்து கம்பேர் பண்றீங்க. ஃபர்ஸ்ட் என்ன பண்ணனும் அப்படினா, it has to satisfy the condition. என்ன கண்டிஷனை satisfy பண்ணனும் அப்படினா, this voltage must be less than the value of, நீங்க collector to emitter voltage வந்து கால்குலேட் பண்ணதுக்கு அப்புறம் செக் பண்ணி பார்க்கணும் with this VCC. This is condition number 1, less than the value of VCE. Second, you have to compare this value with the saturation voltage, whether the value of VCE is greater than saturation voltage or not. Actually, transistor வந்து saturation region இருந்தா அங்க எவ்வளவு voltage இருக்குமோ அது 0.2. அதை விட நம்மளோட voltage நம்ம கால்குலேட் பண்ண voltage அதிகமா இருக்கா இல்லையா? If these two conditions are satisfied, then generally what we can write is, okay, so the collector to emitter voltage is actually it is less than VCC. At the same time, it is also greater than the value of collector to emitter saturation voltage. See, transistor saturation region இருந்தா தான 0.2 வரணும். அதுதான் transistor regionல, அப்ப saturation regionல இருந்தா 0.2 வரணும். 0.2 விட அதிகமா இருக்குன்னா saturation regionல இல்லன்னு அர்த்தம். So simply what you can write your answer is transistor will be in active region only, sir. No issues with this. Further, you can also write this. Suppose, sir, what I did is, நான் வந்து என்ன பண்ணிட்டேன் அப்படின்னா saturation region வழியா போயிட்டேன். நீங்க இது வந்து active region assume பண்ணிட்டு travel பண்ணா ஓகே. இல்ல சார், நான் வந்து ஸ்டார்டிங்ல என்ன பண்ணிட்டேன், transistor வந்து saturation regionல இருக்குன்னு assume பண்ணிட்டேன். When you are assuming that the transistor will be in saturation region, then you will be requested to calculate the value of collector. அப்ப saturation regionல இருக்குன்னு assume பண்ணினா நீங்க என்ன பண்ணுவீங்க? You can fix the value of collector to emitter voltage as 0.2. Yes or no? நான் தானே சொன்னேன். அப்ப saturation region அப்படின்னா ideally you can fix it. Just VC ஓட வேல்யூ வந்து 0.2 ன்னு வச்சுக்கணும். ஆனா நீங்க active regionல இருக்கும்போது இந்த ரிலேஷன்லாம் யூஸ் பண்ணணும். In saturation you are not supposed to use this relation. You can't use this in saturation. Just go ahead. VC equal to 0.2 ன்னு fix பண்ணிட்டு calculate the value of collector current saturation collector current. Why I am putting collector to saturation? Collector current இப்போ நான் saturation region ல இருக்க collector current அப்படின்னு எழுதுறேன். Why? Sir, how can you write this? Because நான் தான் எடுத்துக்கிட்டேன். collector to emitter voltage வந்து நீங்க 0.2 fix பண்ணிட்டீங்களா? 0.2 means that is saturation region voltage. So இதை யூஸ் பண்ணி when you are trying to estimate the value of collector current. So now what you have to do is இதை calculate பண்ணதுக்கு அப்புறம் normal in active region what can be the expected value of collector current? Active region normal acceleration, this same flow. இதை compare பண்ணும்போது suppose if the value of collector saturation current is higher than the value of collector current. நார்மலா நம்ம collector current calculate பண்ணிட்டு saturation region இருக்க collector வழியா போற current normal regionல போற collector current அதிகமா இருந்தது அப்படின்னா you no need to further about it. So what you can write it, once again you can write the transistor will be in active region only, sir. Most of the guys people are what you doing is இந்த கரண்ட் கால்குலேட் பண்ணதுக்கு அப்புறம் சார் சேச்சுரேஷன் கரண்ட் இருக்க வேல்யூ தானே கலெக்டரோட கரண்டோட அதிகமாக இருக்கு, அப்போ இது சேச்சுரேஷன் ரேஞ்சில் தானே சார் இருக்கு. இட் இஸ் ராங் ஆன்சர் ஆக்சுவலி. ஜஸ்ட் அப்சர்வ், இட் இஸ் a simple derivation. we are just cross checking. செக் பண்ணி பார்க்கும்போது டிரான்சிஸ்டர் ஆக்டிவ் ரீஜன்ல இருந்தது அப்படின்னா இட்ஸ் அப்சர்வேஷன். செக் பண்ணி பார்க்குறாங்க. இப்போ டிரான்சிஸ்டர் வந்து சார் நார்மலாக அது ஆக்டிவ் ரீஜன்ல இருக்கும்போது அதில் வந்து ஒரு 3 ஆம்பியர் போயிட்டு இருக்கு சார், சேச்சுரேஷன்ல இருந்தால் 6 ஆம்பியர் போகுது சார். அப்ப என்ன கண்டுபிடிக்கிறாங்க அப்படின்னா சேச்சுரேஷன் கரண்டோட வேல்யூ வந்து கலெக்டரோட கரண்டோட எப்பயுமே அதிகமா இருக்கு. டிரான்சிஸ்டர் when it is in saturation region, the current carried by the current transistor is always higher than the normal value. So what you have to do is they are fixing, okay, if the saturation collector current value is greater than the value of collector current, then we can fix that the transistor will be in active region only. Don't write that blindly this is in saturation region. They are comparing, it's all observation. Saturation current value இதோட அதிகமா இருக்கா, ஓகே டிரான்சிஸ்டர் will be in active region only. If it is in, no sir, ஆப்போசிட்ல நடக்குது. நார்மல் கேஸ்ல கலெக்டர் கரண்ட் வந்து 4 ஆம்பியர் கால்குலேட் பண்ணுது, அதே நான் சேச்சுரேஷன் ரீஜன்ல டிவைஸை கால்குலேட் பண்ணி பார்க்கும்போது எனக்கு 2 ஆம்பியர் தான் சார் வருது. அப்ப என்ன அர்த்தம், when normal case is greater than this value, that in that case only transistor will be entering into saturation region. Saturation அப்படின்னா drained, you can assume like this, it is draining. ஸோ அப்போ அதோட வேல்யூ வந்து எப்பவுமே எப்படி இருக்கும் அப்படின்னா இட் இஸ் லெஸ் தென் தி வேல்யூ ஆஃப் ஆக்டிவ் ரீஜன். அப்படி இல்லையா, இல்லை சார் எனக்கு இது எதுவுமே ஞாபகம் வரல, கேரக்டரிஸ்டிக்ஸை மைண்டில் வச்சுக்கோங்க. நான் அவுட்புட் கேரக்டரிஸ்டிக்ஸ் வரைஞ்சேன் இல்லையா காமன் கலெக்டருக்கு, என்ன வரைஞ்சேன், இப்படி தானே நம்ம வரைஞ்சோம். வரைஞ்சிட்டு நான் என்ன சொன்னேன், இதுதான் சேச்சுரேஷன் ரீஜனும் இதுதான் ஆக்டிவ் ரீஜன் நான் தானே சொன்னேன். ஆமாம் சார். If you remember this too, what you can say, see, this is saturation region, this is active region. இதில் யாரோட வேல்யூ அதிகமாக இருக்கா, the current that is flowing through active regionல போற current வந்து saturation current அதிகமாக இருக்கு. So what you can say, when the value of saturation current is less than the value of active current, then transistor will be in saturation region. No sir, saturation region current is higher than the value of collector current, means it is shifting its domain, it is trying to active in active region, it is trying to enter into active region. So அப்ப saturation current value collector current அதிகமா வருதுங்கிறப்ப it actual mean is your device is trying to operate at an active region. That's all. Okay, do remember like this, don't get too much of confusion with this. Fine sir, I hope now you might understood how to do these things. And the saturation region I have written the conclusion. You can also write like this. நீங்க saturation current வந்து calculate பண்ணிட்டு இருக்கும்போது suppose sir I have estimated the value of beta. Beta ஓட வேல்யூ வந்து suppose if it is greater than or equal to collector current divided by minimum. See example question வந்து sometimes என்ன பண்ணுவாங்க அப்படின்னா range of beta will be given. They will be giving you certain range, beta minimum to beta maximum. It's better to write in this way. ஸோ அந்த மாதிரி கொடுக்கும்போது என்ன பண்ணுறீங்க அப்படின்னா டோன்ட் மேக்ஸிமைஸ் தி வேல்யூ, ட்ரை டு கோ ஃப்ரம் மினிமம் வேல்யூ, சப்ஸ்டியூட் தி மினிமம் வேல்யூ, சப்ஸ்டியூட் பண்ணிட்டு இஃப் தி வேல்யூ ஆஃப் பேஸ் கரண்ட் இஸ் கிரேட்டர் தென் ஆர் ஈக்குவல் டு கலெக்டர் கரண்ட் டிவைடட் பை மினிமம் வேல்யூ ஆஃப் பேஸ் கரண்ட். இதை பீட்டாவால் டிவைட் பண்ணி நீங்கள் செக் பண்ணும்போது இஃப் திஸ் ரிலேஷன் இஸ் சாட்டிஸ்ஃபைடு தென் ஆல்சோ யூ கேன் ரைட் த டிவைஸ் வில் பி இன் சேச்சுரேஷன் ரீஜியன். Directly you can write. If this condition is invalid, then you can go to the opposite. Another one is what? Active region. No sir, this condition is invalid, so device will be in active region. That's all, right? So do remember, why I am telling all these things is, in the examination, we can't give assurity that what type of data that they are giving. So it is better to learn in all possibility way. Sir, understand you this சொல்றீங்க அதை சொல்றீங்க, how can you do all these things sir? I will forget, or it is too difficult to do these all things. No, I am not asking you to do all these things. மொத்தமா 3 தானே சொன்னேன். Yes, totally I said only 3 things. If you solve some 4 to 5 questions, you will be understanding actually how it is working. Finish. அவ்வளோதான், உங்களுக்கே புரிஞ்சிடும் அதுக்கப்புறம். Then you no need to remember anything. Just by solving the question, it will be registered in your mind. Okay, fine, sir. So I hope you understood all the basics. So finally, I would like to say, in our transistor, so far whatever we did, that is called DC analysis. In conclusion, let me make one more thing. நான் இது வரைக்கும் மேக் பண்ண எல்லா கன்க்ளூஷனுமே வந்து என்ன அப்படின்னா, ஒரு டிசி சப்ளை நம்ம டிரான்சிஸ்டர் கூட கனெக்ட் பண்ணால் என்ன நடக்கும் அப்படிங்கிறது மட்டும்தான். இது நம்ம என்ன பண்ண போகிறோம் அப்படின்னா, பேசிக்காக இந்த டிசி சப்ளை வச்சு நம்ம டிரான்சிஸ்டர் வந்து ஆப்ரேட் பண்ண போகிறதில்ல மோஸ்ட் ஆஃப் தி பிளேசஸில். சாரி, தேர் ஆர் சோ மெனி அப்ளிகேஷன். ஒன் ஆஃப் தி அப்ளிகேஷன் இஸ் டிசி சப்ளை வச்சு நம்ம பண்ணும்போது, இப்போ பேசிக்கலி வி ஆர் டிசைனிங் சம் ஸ்விட்சிங் ஸ்கீம்ஸ், நம்ம இதெல்லாம் பார்த்துருப்போம் இல்லையா. நான் டிஜிட்டலில் நம்ம இதை யூஸ் பண்ண போகிறோம் அப்படின்லாம் சொல்லியிருப்பேன், ரைட்? ஸோ வாட் எவர் தி கன்க்ளூஷன்ஸ் தட் ஐ மேட் சோ ஃபார், தட் இஸ் எவ்ரி திங் ஐ டிட் ஜஸ்ட் வித் தி ஹெல்ப் ஆஃப் இப்போ இன்புட்டில் டிசியை கனெக்ட் பண்ணி வி ஹவ் பீன் அப்சர்வ்ட் ஆல் தீஸ் திங்ஸ். ஸோ டிசி கேரக்டரிஸ்டிக்ஸில் வந்து என்ன பண்ணுவாங்க அப்படின்னா, அவர் டிரான்சிஸ்டரில் வி ஆர் ஹேவிங் எ பாயிண்ட், ரைட்? ஸோ தட் இஸ் அவர்